For Chapter 18 Reassessment, I chose to work different situations from web assignment. The Coulomb's law is an equation of the electric field of a stationary point charge. Experiments have also shown that a moving point charge makes both an electric and magnetic field, which is where this law comes into play. For my first problem of homework 18.3, there is a straight wire with length 68 centimeters and a conventional current. I want to find the magnitude of the magnetic field due to this wire at a location 2.7 centimeters away. For this example, I wanted to compare the results of the exact value to the approximate value. First, I found the expression of the relationship between these two equations. I found the values for both equations, and by using the expression of the relationship between the two, I found that all answers agreed with each other, which means that the exact and approximate equations differ by a value of 0.9968 for this situation. For my next problem, I have this diagram. The problem wants me to find delta V at a location A due only to the current of segment 1 of the wire. I found delta L by dividing the length by 8, which equals 0.225 meters. And because the wire is along the x-axis, I know that the delta L vector would only have magnitude of 0.225 meters in the x direction. Next, I found the location of the center of segment 1 and used that vector value to find R and the unit vector. Then I found delta L cross R. Finally, I used the equation of a short wire to find delta B at a location A due only to the current in segment 1. My next two examples are very similar. The first example is a current-carrying wire on top of a compass aligned with the original direction of the needle. The wire is 4 millimeters above the needle, and the needle deflects 13 degrees. To work this problem, I first determined that the electron current in the wire was flowing north, which means that the conventional current in the wire flows south. Using the right-hand rule, I am also able to determine that the magnetic field under the wire due to the current points east. By then using the magnetic field equation of a wire, where the value of V is affected by the value of tan theta, I was able to find the amount of conventional current flowing through the wire. For the next problem, there is a long current-carrying wire oriented north to south, lying on a table. The compass is on top of the wire with the needle 3 millimeters above. The compass deflects 14 degrees to the west, and I want to find the magnitude of the magnetic field in direction at A due only to the current in the wire. Just as I did in the previous problem, I found the conventional current by using the magnetic field equation of a wire, where V is multiplied by tan 14. I use this conventional current I found in the same equation, where R now equals 2.7 centimeters, to find the magnetic field at A to be towards the ceiling, which is perpendicular to the top. Finally, I chose a homework problem from 18.4 to sum up all the ideas of this reassessment. As illustrated in the diagram, there is a compass at the origin, which despite the presence of the magnet in the coil, points north. Along the x-axis is a magnet with a dipole moment of 0.48 amperes meter squared. The center of the magnet is 21 centimeters from the center of the compass. Between the compass and the magnet is a coil of wire with radius 1.5 centimeters. The center of the coil is 9.1 centimeters from the center of the compass. The steady current is a little more than 1 ampere and runs clockwise when viewed from the compass. Because the compass is not affected by the magnet and the coil, I know that the magnitude of the magnetic field for each of these objects must be equal, and the direction must be opposite, which also means that the net magnetic field at the location of the compass equals the magnetic field of the Earth. In order to determine the number of turns in the coil, I first found the magnetic field of the magnet and the magnetic field of one loop of coil. Because not all parts of the magnet are the same distance from the compass, I am able to treat the magnet as a dipole along the axis to get an approximation. After finding both values, I divided the magnitude of the magnetic field due to the magnet by the magnitude of the magnetic field due to one loop of coil, to find that for this situation to be true, the coil must have 51 turns.